Monte Carlo is a family of randomized algorithms for approximating the exact values. I'm going to use a few examples to introduce Monte Carlo algorithms. The first example is calculating pi using uniform sampling. We already know that pi is approximately 3.14159. Now let's pretend that we don't know the value of pi. Can we find it out approximately using a random number generator? Let's use Monte Carlo to approximate pi. The idea is uniform sampling. Assume we have a random number generator that can generate numbers uniformly distributed between -1 and +1. Each time, we generate two numbers, x and y. In this way, each time we uniformly sample one point from the blue square. Everywhere in the square has the same probability density. The green circle is contained by the blue square. The circle is centered at the origin and has a radius of 1. A randomly generated point may fall inside the circle and outside the circle. Both are possible. Think of this question. What is the probability that point xy is inside the circle? Let me ask the question in another way. If 1 trillion samples are randomly generated, then how many will fall inside the circle? Because the points are uniformly sampled, the probability is the area of the circle divided by the area of the square. The sides of the square have length of 2, so the square has an area of 2 square, which is equal to 4. The circle has a radius of 1. Its area is pi r squared, which is equal to pi. The ratio of the two areas is pi over 4. Thus, a uniformly sampled point, xy, falls inside the circle with probability p equal to pi over 4. Here, pretend that pi is unknown, and we seek to find pi. Let's uniformly sample n points from the square. Every point falls inside the circle with probability p, and this process is repeated n times. Thus, in expectation, the number of points in the circle is pn equal to pi n over 4. Be careful, this is the expectation, not the actual outcome. If you sample 5 points randomly, all of the 5 points can be outside the circle. This can happen. Another question. Given a point xy, how do you know whether xy is inside the circle? It's actually easy to tell whether it is inside or outside. Simply use the equation of the circle. If x squared plus y squared is less than or equal to 1, then we know the point is in the circle. We have sampled n points uniformly at random. After completing the simulation, we found that there are n points in the circle. If n is big, then the actual observation m should be close to the expectation pi n over 4. Note that pi n over 4 is the expectation, while m is the actual observation. The two are usually different. They are close if n is big. Let's move n to the denominator. Then we obtain this equation. Pi is close to 4m over n. This is the equation we use for approximating pi. The law of large numbers guarantees that as n grows to infinity, the estimate 4m over n approaches pi. We can actually use concentration inequalities to bound the approximation error. The approximation error is inversely proportional to square root n. This means as n grows, the Monte Carlo estimate becomes more accurate. But such a convergence rate is slow. If n is 100 times larger, the error is only 10 times smaller. In the next lecture, we will use a concentration inequality to analyze Monte Carlo. This is our conclusion. A total of n points are sampled from the square. We observe n points in the circle. We approximate pi by 4m over n. Note that the sampling must be uniform. You need to make sure that everywhere in the blue square has the same probability. If the sampling is not uniform, then the equation cannot be applied. With the equation, we are ready to write a computer program for estimating pi. I'm going to show the pseudocode. Firstly, the user needs to specify the number n. Big N can make the accuracy high, but big N means heavy computation. It's a trade-off. M is for counting. Initialize M to be 0. Secondly, repeat the random sampling n times. In each round, sample a point x, y uniformly at random. X and y are both from the interval between 0 and 1. If the point x, y is in the circle, then increment n by 1. After step 2, we know the number of points inside the circle. The number is m. Finally, return the estimate of pi using m and n. Pi is approximately 4m over n. Another example is Buffon's needle problem. It's also a Monte Carlo method for calculating pi. Buffon was born in 1707. He was born about half a century later than Newton and Leibniz. In Buffon's time, calculus was already popular. The people knew integrals. Buffon's needle problem is about using Monte Carlo to calculate pi. Unlike our previous example, Buffon's needle problem does not rely on a random number generator. You can draw parallel lines on paper and then throw needles. Then, count the number of needles that lie across the parallel lines. Such an experiment can be performed without using a computer. To perform the experiment, let's first draw many parallel lines. Two neighboring lines have a distance of d. Prepare some needles of the same length. Let the length be L. Randomly throw a needle on the paper. The needle has a length of L. The needle may or may not lie across a line. This needle lies across a line. Throw another needle. This one may not lie across a line. Assume the location and angle of the needles are uniformly distributed. Then, with probability p equal to 2L over pi d, a needle lies across a line. The probability is related to pi. That's why we can use this equation to approximate pi. This equation can be proven using integrals. Recall that calculus was invented by Newton and Leibniz. They were about half a century older than Buffon. Calculus was very well known in Buffon's time. It's not hard for them to find the probability is p equal to 2L over pi d. The equation is very intuitive. Using longer needles, the probability goes up, which means a needle is more likely to lie across a line. If the distance between the lines increases, then it's less likely for a needle to lie across a line, so the probability will go down. We know the probability is P equal to 2L over pi d. Now, let's use this equation for calculating pi. We can randomly throw a needle onto the paper and repeat this process n times. Each needle lies across a line with probability P. The experiment is repeated n times, so in expectation, Pn needles lie across the lines. Using the probability P we derived, we have Pn is equal to 2ln over pi d. This is the expectation. Suppose we observe m needles across the lines. If n is big, then the actual observation m should be close to the expectation. The expectation is the right side of the equation. We use this equation for estimating pi. Let's move m to the denominator and pi to the numerator. Then we obtain this equation. Pi is approximately 2ln over dm. Using m and n, we obtain an estimate of pi. Many people have actually conducted experiments. They have thrown hundreds or even thousands of needles. Their estimates of pi are not far from 3.14. Among them, this guy's result is too good to believe. People don't trust his result. Concentration inequalities show that the convergence rate is square root n. It means if n becomes 1 million times larger, then the error is 1,000 times smaller. He repeated the experiment only 3,400 times. Even if he repeated the experiment 1 billion times, the precision could not be that high. You can write a Python program to simulate the experiment. You can sample a point uniformly at random. The needle's head is at the random point. Then, randomly sample a number between 0 and 360. The random number is the needle's angle. Using the point and angle, the needle is uniquely determined. The third application is to calculate the area of a region. You may have seen this math problem. There is a square, a circle, and a sector. You are asked to calculate the area of the grid region. I don't know how to directly calculate the area without using calculus, but I can approximately find the area using Monte Carlo. Monte Carlo is based on random sampling. We sample points uniformly at random from the square. A point in the square can be inside or outside the circle. We can use the circle's equation to find whether a point is inside or outside. The circle is centered at the point 1, 1, and its radius is 1. So the equation of the circle is this one: x minus 1 squared plus y minus 1 squared is less than or equal to 1. If a point is in the circle, it must satisfy the equation. Using the equation, we can tell if a point is in the circle. Note that if a point is in the grid region, it must be outside the blue sector. All points in the sector must satisfy this equation. X squared plus y squared is less than or equal to 2 squared. It is a circle centered at the origin and with a radius of 2. A point xy in the shadow must satisfy the two conditions. First, it must be inside the circle. Xy satisfies that x minus 1 squared plus y minus 1 squared is less than or equal to 1. Second, the point must be outside the quarter circle. Thus, xy satisfies that x squared plus y squared is greater than 2 squared. All points satisfying the two conditions are in the gray region. We sample points from the square uniformly at random. Everywhere in the square is sampled with the same probability. Let's calculate the probability. The sides of the square have length of 2. So the area of the square is a sub 1 equal to 2 squared equal to 4. Denote the area of the gray region by a sub 2. A sub 2 is what we seek to find. A point uniformly sampled from the square falls inside the gray region with probability p equal to a2 over a1 equal to a2 over 4. Let's uniformly sample n points from the square. The number n is up to the user. A big N is good for accuracy, but bad for computation. There are a total of n randomly sampled points. Each point falls in the gray region with probability p. Thus, in expectation, np points falls in the gray region. The probability p is equal to a2 over 4. So np is equal to na2 over 4. It is the expected number of points in the gray region. We can write a program to randomly sample points. We observe n points in the gray region. If n is big, then m is close to na2 over 4. Recall that m is the actual observation, and na2 over 4 is the expectation. Equivalently, the area of the gray region A2 is approximately 4m over n. We use it as an estimate of the area. I'm going to explain the pseudocode. First, specify the number n. Bigger n will make the result more accurate, but it will incur heavier computation. M is a counter. Initially, reset m to 0. Secondly, repeat the simulation n times. Uniformly sample x and y from the interval between 0 and 2. Equivalently, the point xy is uniformly sampled from the square. We need to judge if a point is in the gray region. If a point is in the circle and outside the quarter circle, then it is in the gray region. If both of the equations are satisfied, we know the point is in the gray region, so we increment m by 1. Finally, return 4m over n as the estimate of the area of the gray region. The fourth application is Monte Carlo integration. It has extensive applications in science and engineering. Here is an example. We are given a sophisticated function like this one. F is equal to 1 over 1 plus sine of x times log of x squared. We are asked to calculate the definite integral. It is the integral of function f on the interval from 0.8 to 3. Honestly speaking, I don't know how to calculate the integral analytically. I don't even know whether an analytical solution exists. Many science and engineering problems require integration. Oftentimes, the function f is highly involved. Sometimes, there is no way to analytically calculate the integral. So people resort to Monte Carlo for an approximate solution. Let's begin with the easiest problem, Monte Carlo integration for univariate functions. Univariate function means that the variable x is a scalar. Given a univariate function fx, we are asked to calculate the integral of fx on the interval from a to b. Denote the integral by I. Monte Carlo integration approximately calculates the integral in 3 steps. First, draw n random samples from the interval a to b uniformly at random. Let the samples be scalars x sub 1 to x sub n. Second, evaluate the function f of x sub I for all I from 1 to n. Take the average of the n function values. Scale the result by b minus a. Denote the outcome by q sub n. Finally, return q sub n as an approximation to the integral I. The correctness of Monte Carlo integration is guaranteed by the law of large numbers. As the number of samples n grows to infinity, the estimate Qn is equal to the actual integral I. We can further use concentration inequalities to find the convergence rate. We can show that the difference between Q sub n and I is inversely proportional to square root n. Let's study this problem. We are given the function fx, which is very involved. We want to calculate the integral of fx on the interval from 0.8 to 3. It is very hard to do the calculation analytically. Perhaps an analytical solution does not even exist. A feasible approach is Monte Carlo integration. First, draw n random samples from the interval between 0.8 and 3. Denote these samples by x sub 1 to x sub n. Second, evaluate the function values for all x sub I. Average the n function values and scale it by 2.2. Here, 2.2 is the size of the interval between 0.8 and 3. Finally, return q sub n as an approximation to the integral. We have learned Monte Carlo integration for univariate functions. Now, let's do it for multivariate functions. Multivariate functions are functions of vector variables. Denote the vector variable by vector x. We want to calculate the integral of fx on the set omega. Analytically calculating the integral of multivariate functions is way harder than the univariate functions. Oftentimes, an analytical solution does not exist. Monte Carlo is perhaps the most useful method for computing high-dimensional integrals. We do Monte Carlo integration in the 4 steps. First, draw n samples from set omega uniformly at random. Denote them by vectors x sub 1 to x sub n. Secondly, find the volume of set omega. Denote the volume by V. In general, it takes another definite integral for calculating the volume, which is as hard as the original problem. We must avoid calculating the integral. We can make the set omega a simple shape, such as cube and a ball, so that the volume can be easily found. Thirdly, evaluate the functions for all x sub I, and then take the average. Then, scale the average by the volume V. Denote the outcome by Q sub n. Finally, return Q sub n as an approximation to the integral I. I'd like to use this bivariate example to demonstrate Monte Carlo integration. I will use Monte Carlo integration to derive an algorithm for calculating pi. We have done exactly the same for approximating pi. The derived algorithms are the same, but the derivations are different. Define f as the bivariate function. It has two variables, x and y. If the variable x, y is in the green circle, then the function value is 1. Otherwise, the function value is 0. Define set omega as a blue square. We will draw random samples from omega. The set omega is up to the user. The set omega can be any shape, as long as it contains the green circle. But we had better make omega a simple shape. Otherwise, we won't be able to find its area or volume. A question: what is the integral of fxy on the set omega? Obviously, the integral is the area of the circle. The area is pi r squared. The radius r is 1. So the area is equal to pi. Monte Carlo can approximate the integral I. Since I is equal to pi, the result of Monte Carlo integration is an estimate of pi. Now, let's perform Monte Carlo integration. Step 1 is random sampling. We draw n samples from the set omega uniformly at random. Let the samples be x1, y1 to xn, yn. Step 2 is calculating the volume, V. Since the variable is two-dimensional vector, V is area instead of volume. The set omega is a blue square. Its sides have length of 2, so its area is equal to 4. Step 3 is to evaluate the function f for all the endpoints. Take their average, and then scale it by V. Denote the outcome by Q sub n. Finally, return Q sub n as an approximation to the integral I. We know the integral is equal to pi, so Q sub n is an approximation to pi. The algorithm here is the same as what we derived at the beginning of this class, but the algorithm derivation is different. The last application is the Monte Carlo estimate of expectation. It is particularly useful for statistics and machine learning. Define uppercase X to be a d-dimensional random variable. People typically use uppercase for random variable and lowercase for its observation. Let Px be a probability density function, or PDF. It describes the probability density at point x. It has such a property. The integral of Px on the entire space is equal to 1. Here are some examples of PDFs. The PDF of the uniform distribution is Px equal to 1 over t for x in the interval between 0 and t. Everywhere on the interval from 0 to t has the same density. The PDF of univariate Gaussian distribution is this function. It is determined by the mean mu and the standard deviation sigma. Let fx be any function of a vector variable. The expectation of fx is defined in this way. X is treated as a random variable. Its PDF is function p. It is equal to the integral of fx by px on the entire d-dimensional space. Directly and analytically computing the expectation is not easy, especially when x is high-dimensional. So in practice, the expectation is approximated by Monte Carlo. Monte Carlo estimate of expectation works in the 3 steps. First, random sampling. Draw n random samples from probability distribution Px and denote them by vectors x sub 1 to x sub n. Note that here we do not perform uniform sampling. Instead, the samples are drawn from the distribution Px. For commonly used distributions such as Gaussian distribution, there are existing libraries for programming implementation. Python and MATLAB provide functions for sampling from all the commonly used distributions. The second step is evaluating the function values for all xi and averaging the function values. Denote the average by q sub n. Lastly, return Qn as an approximation to the expectation. The larger n is, the more accurate the estimate is. I have finished the technical content of this lecture. In the end, I'd like to discuss the name of Monte Carlo and other randomized algorithms. The name Monte Carlo is from the Grand Casino in Monaco. The casino is 1.5 century old. It's very famous. The term Monte Carlo method was firstly introduced in 1947 by Nicholas Metropolis. Nicholas Metropolis was one of the greatest statisticians. If you are familiar with statistics, you must have heard of his name. The term Monte Carlo refers to algorithms that rely on repeated random sampling to obtain numerical results. Monte Carlo is a family of randomized numerical algorithms. The outputs of Monte Carlo algorithms can be incorrect, and they are typically incorrect. In all of our examples, the algorithm's outputs are incorrect. For example, when approximating pi based on thousands of Monte Carlo samples, the result is around 3.1 and 3.2. They are never the same as the exact pi value. Nevertheless, the inexact results are useful, and they are close to the correct solution. In many statistical and machine learning applications, a low precision estimate is good enough. Monte Carlo is a kind of randomized algorithms and perhaps the most well-known randomized algorithms. Besides Monte Carlo, there are many types of randomized algorithms. Las Vegas algorithms are randomized algorithms that always produce the correct answer. For example, randomized quicksort is a kind of Las Vegas algorithm. The quicksort algorithm is random, but it always outputs the correct answer. The randomness does not hinder the correctness. People love to name randomized algorithms after casinos. Monte Carlo and Las Vegas are both famous for gambling. Atlantic City is also famous for gambling. Atlantic City algorithms are polynomial time randomized algorithms that answer correctly with probability greater than 75%. If you repeat an Atlantic City algorithm many times, the success probability will approach 100%. I have finished this lecture. Thank you for watching. The link to slides can be found below the video.